Welcome back to Wood Engineering. I'm Jeff Barochko from Carleton University, and in this video we're going to continue our example calculating the strength of this connection that has a timber beam connected to two parallel timber cross bracing elements in a three-member connection. So in the previous video we calculated all the spacing requirements, and then we did the check for yielding resistance. And we found that the yielding resistance of this connection, after we checked all the Johansson yield equations, was 5.8 kilonewtons. And now we're going to move on and calculate all of the strengths on the beam side of the connection. So in this connection, since both sides of the connection are timber, we have beam on one side, and then we have two braces on the other side. Okay, basically on the other side of the load of the bolts. So the bolts are being pulled one way by the beam and in the opposite direction by the two braces. And so those are the two sides of the connection. And so we have to check both sides separately. So I'm going to start with the beam resistances, and we'll start with the row shear resistance. And then after that, we will do all the brace resistances. So let's get started. Okay, so as we know, in the beam, we have our bolts being loaded on an angle from the brace. So the brace is pulling the bolts up and to the right. And so they are loading the bolts, and the bolts are loading the beam in some direction at an angle to the grain. So there's a parallel to grain component, pardon me, and a perpendicular to grain component to that force. So when we do our parallel to grain resistance checks, like the row shear resistance or the net tension resistance, we will be checking those against the parallel to grain direction of the force, and vice versa for the perpendicular to grain resistances, which we'll check against the perpendicular to grain component of the force at the very end. Of course, there's also going to be an interaction between those two, which we will check against the total load NF. But we're going to do that later. So for right now, we're just checking all the resistances. As I mentioned in the first video, we still have row shear in this connection, even though we don't have a loaded edge, which means basically the plug in between these two. So if I'm looking at the beam, I'm talking about this member back here. So in between these two, so the rows are like this. You know, we have shear planes like this, and we can basically fail this plug as the bolts want to move in this direction, right? Which is the horizontal component of the diagonal force. And so we can still fail that plug in between the two bolts, and that failure of that shear plug in between the two bolts will cause basically failure of the connection. Of course, we'll also have to have some local embedment failure, which is not explicitly taken into account in the connection, right? We'll have to fail here in embedment, which isn't taken into account in the connection, but is kind of taken into account in a roundabout way by assuming basically that there are two shear plugs that have to fail instead of one in this connection. Okay, so here is our section that we're dealing with for the beam. Okay, so we are dealing with a 38 by 235 SPF number 2. So if I go all the way back to what we used to do, what we learned way at the beginning, I have 38 by 285. So that means it's a structural joist and plank category. So that's going to be table 6.3.1a. That's the number from 08614. Then I look for SPF number 2. This is where I'm going to get all of my strengths from. Okay, so those I'm going to lay out here. Okay, so that's how we get our FV, which is our shear strength. Our KLS, which is to account for non-uniform stress distribution in the members for the beam, is going to be 1.0 because it's a center member. And refer back to the bolted connections video to learn more about KLS. Okay, so since it's the member in the center, KLS equals 1. For the side members, it's not going to be 1. The thickness of this member is 38 millimeters. Okay, this is a 2x10, 38 millimeters. And we're going to need our number of fasteners per row, which is 2. So our row is in the horizontal direction, so there are 2 bolts there inside that row. And our ACRI is going to be SR, which in this case is, or SP if we're talking about 08619, which is 99 millimeters. These are all of the inputs that go into our PR equation, our basically individual row shear strength equation. And usually this has to be the minimum of the in-row spacing or the loaded end distance, but in this case we don't have any loaded end distance. Okay, so now we can calculate our PR. We would call that 1, 1 for member 1, row 1. You remember this equation. Okay, so we have all these values, 1.5, 1.0. Now this is not KSF anymore, it's KSV, which is our service condition factor for shear, which is 0.96. KLS 1.0, T38, and I multiply all of these numbers together, and I'm going to get 13 kilonewtons. Okay, and that's our only row for row shear for the beam, because the beam only has 1 row in the parallel to grain direction. Remember, for the brace, we decided that we have to consider it as 2 rows. Okay, so the minimum resistance of any row is, there's only 1 row, so that's easy. And then now I can find the total factored shear resistance, row shear resistance. So NR is the number of rows. So again, we only have 1 row in the parallel to grain direction for the beam. And so NR equals 1. And so our PRR is phi W times our minimum row shear resistance times our number of rows, and we get 9.1 kilonewtons. Okay, so now, so that's for member 1 of that side of the connection. There happens to be only 1 member on this side of the connection. So usually we have to take the sum of all the members on that side of the connection. In this case, there's only 1 member on that side of the connection. So my PRRT for the beam, my total row shear resistance for the beam side of the connection is just 9.1 kilonewtons. Okay, let's, I'm going to make a note about group tear out. There's not going to be any group tear out because we're not at a loaded end. Okay, so since there's no loaded end to pull any, group tear out plug out of the end, then we can't have group tear out. Okay, so those are the first 2. So these are all parallel to grain ones, right? Row shear is a parallel to grain phenomenon. Group tear out is parallel to grain phenomenon. Last one is net tension for parallel to grain. Okay, so I've put a big note here, just big asterisks. So we're checking net tension, okay, but I'm basically assuming that all of the tension in the beam is being caused by the brace and there's no other tension. So if I look back here, I have this load which causes a tension in the beam, right? Which means there must be some reaction over here. But it is possible in a real case or any other case, there might be other tension loads in this beam. Like if this is part of a truss, for example, then there might already be a tension on the right side of the brace that is caused by, other actions in general, which would make this then become even bigger to be in balance with that. So right now I'm assuming that those loads don't exist because they're not specified. Okay, but it's just a warning that if I'm checking net tension in the beam itself, I need to consider all of the tension loads that are on that beam, not just one that comes from whatever brace is immediately at that location. Okay, but I'm going to assume that that's the only net tension load. Okay, so FT, our tension resistance for this lumber, is 5.5, which I got from table 6.3.1a, just like I did for FV. Okay, let's check all of the gross and net areas now. And we're also going to check our net section requirement. Okay, so here's the gross area. Okay, so for the net area, I'm going to remove one hole because I'm talking about a area across the section. So if I'm looking at my beam, obviously, so this is a net section here. And so across that net section, I have one hole. So I'm just going to remove one hole in the calculation. And so you can see it doesn't really make much difference. If I remove if I find what percentage is removed, it's 6.4%, which is less than 25%. So therefore we're okay on that requirement. And now I have my net section area, which I'm going to need to calculate my strength. So remember that calculating the net area in tension is the same as what we covered in one of the first lectures. So it's just net area times our tension strength times a size effect factor. Okay, we find our modified strength, our modified tension strength, capital FT. Our size effect factor, which we're going to get from our size effect factor table, which maybe we haven't seen in some time. So remember, this is 38 by 230. So it's 38 by 235. So larger dimensions 235. So our size effect factor KZT is 1.1. And therefore our TNR1, our total net tension, is just our regular net tension strength. And we get 38.2 kilonewtons. And then we need to find the net area, that the net tension strength of all of the members on that side of the equation, of the connection, on that side of the connection. And in this case, for the beam, there's only one member on that side of the connection, which is the beam itself. Okay, so usually this is a sum for multiple members, however many there are, and in this case there's only one, so it's just the strength of that member by itself. So you can see the net tension strength is much higher than even the row shear strength, which was 9.1, which in turn was much higher in this case than the yielding resistance of 5.8. So far, it seems that the yielding resistance is governing. Until now, because now we're going to look at the splitting resistance, which, as we know, is one of the weakest ways that we can load a piece of wood. And this splitting resistance exists because the beam has a perpendicular to grain component to the load from the bolts, that the bolts are loading the beam. Okay, so for this we need our thickness. Again, we need millimeters. We need our total depth, which is 235. And we need our EP, which is our unloaded edge distance. So you'll recall way back our unloaded edge distance. So here's our beam. We're looking at splitting of the beam. Here are the loads from the bolts onto the beam. The beam will split like this, right? And separate. And we need our unloaded edge distance. This is our unloaded edge, and the unloaded edge distance is 100 millimeters. Okay, so therefore our effective depth, DE, for this equation is D minus EP, which is 235 minus 100. It's basically the load from the farthest bolt to the loaded edge. And here we get 135 millimeters for our effective depth. We have a phi factor of 0.7 for this brittle failure mode. And now we can get to calculating our QS and then our QSR. So this is our QSI. So this would be QS1 in this case. 14t square root of like this. And remember that this is from fracture mechanics. Our DE was 135. Okay, and we get a QS1 of 9.5 kilonewtons. Okay, and now we can find our factored splitting resistance. Okay, so as before, 0.7, 9.5 kilonewtons for our QS. And then we have our modification factors. This is a wet service condition. We determined that KSF was 0.67, untreated, and our QSR comes out to 4.44 kilonewtons. Okay, and then there's only one member again on this side, so the splitting resistance is 4.4, which is a bit less than what the yielding resistance was. So we have some inkling that splitting might, in the end, be governing. Okay, so those are all of the resistances for the beam side of the equation. Now we need to go and switch gears and look at the brace side of the equation and do all of the brace resistances, starting with row shear and then doing group tear out and net tension. Now in this case, for the brace, we only have loads that are in the parallel to grain direction, because here are the loads from the bolts onto the brace. They counteract the load on the brace at the top right and F. And this is our grain direction, so those loads are always aligned with the grain. So we won't have any splitting possibility in the brace. So that reduces the number of checks we have to do, although this time we have to do group tear out, so that adds 1. Okay, so let's do all the brace resistances now. Okay, so now we have to do row shear resistance for the brace. Let's remember what our geometry looks like now. Okay, so we previously looked into, are we considering 1 row of bolts or 2 rows of bolts here? Because here is our bolted layout. We decided, does this go like 1 row like this, or does it go 2 rows like this? Based on the relative spacing of the rows and the columns, we decided that it's 2 rows of bolts. So therefore, that means that we're going to have 2 different row shear lines here. And we already determined that this distance, which I'm measuring from the center of the bolt to the center of when the row shears intersect with the edge, is 141 millimeters. And you recall that this was a 45-degree angle. Okay, so that's our row shear length, basically, is going to be our 141. We don't have to take any minimum here because we basically have only one plug to take out. Okay, so this is also SPF number 2, same as before. So that means I'm going to have the same FV 1.5 MPa. This time, since I'm dealing with the side member, my KLS is 0.65. So in the side members, the stress distribution in the side members at the edge of the hole where the bolt is loading it is not uniform. And we compensate for that non-uniformity by reducing the strength, because this is a side member. The T is going to be 25 millimeters. We'll recall this is less than the full width, so the full width was 38, but we have to reduce it because of the countersink, if you remember. We have 1 fastener in each row, so our NC is 1. And remember, we're looking at each row separately here. Our ACRI is going to be equal to AL here. which is 141 millimeters. That's our loaded end distance. Usually it's the minimum of the loaded end distance and the spacing within the row, the parallel to grain spacing. And then we have our PR11. We multiply all these things together and we get 3.96 kilonewtons. And the minimum, so this happens to equal the same for the second row, right? So second row identical. Okay, both of these rows have the same length here, right? That's 141, just like the other one was 141. If we had this one out a little further, like this, for example, and that had a longer AL, then I would again calculate for both rows what is the row shear strength. And then I would take the minimum, which would then be this one, right? If it was closer to the end. Okay, in this case, they are identical. So minimum is PRIJ min is the same 3.96 kilonewtons. Okay, so now I can find the total row shear resistance for member 1. Okay, we have 2 side members, so I'm just doing the first side member for now. We have 2 rows, and therefore my PRR1 gives me 5.54 kilonewtons. Okay, so we have in this 2 different side members. We have this side member here and this side member here. Okay, so we've just gone ahead and calculated for one of them. Now the other one happens to be, in this case, exactly identical. So in that case, I'm going to say that the row shear strength of the second member is the same as the row shear strength of the first member. Now that is not necessarily always going to be the case. That's why it's laid out explicitly in the standard that I calculate for one and I calculate for the other. For example, what if my connection here had a bolt and that bolt only had a countersink on one side but not the other? So on one side the member was actually thicker. Then the thicker one would have a different row shear resistance. So I would have to calculate both separately. Okay, which is not the case here. So here, since they're both the same, PRR2, member 2, equals PRR1, 5.54, and then the total row shear resistance, so PRRT for the brace side of the connection, is the sum of all the PRRIs, right, which is going to be PRR1 plus PRR2, which is 5.54 plus 5.54 equals 11.1 kilonewtons. So that is the total row shear for the brace side of the connection, taking into account both braces and, of course, both rows of row shear in both braces. Okay, so that's the total row shear. Okay, not last, but next, we have to calculate the group tear-out resistance. Okay, so now we're going to do group tear-out. Recall that we have 2 row shears, a row on one side of the group and a row on the other side of the group, and then a tension portion on the top that have to fail for group tear-out. So recall the row shear resistance. So for the first row, it was 3.96. That's for this one, the orange one. And then for the last row, since these rows were the same, the row shear resistance for the last row was the same. Okay, so now we need to deal with the tension area. So our FT is 5.5 MPa. That's for our SPF number 2 for structural joist and plank grade, which we calculated before. We're going to recall that the hole size is bigger than the bolt. Okay, so that's 15 millimeters because we're doing net tension here. So then our APGI, capital APGI, which is our area, our net tension area for that portion between the bolt holes, is 70. So remember, if I go center to center on these bolts, this is 70. Then I have to remove the bolt holes. So 70 minus 2 times the hole divided by 2. So I have 2 half holes that I need to remove. And then I have to multiply that distance by the thickness. This is a very conservative approach here that I'm taking. I'm just going to basically consider that the net area is only for the portion that is not countersunk. So this is accounting for the countersink, that 25 millimeters. And I get 1375 millimeters squared. So I'm basically taking just the thickness, not including the countersunk portion. Okay, and so now I can calculate my PGR1, which is my group tear-out strength. Okay, so we have to be very careful here because we have to remember that we're comparing newtons to newtons, because when I calculate the right side of this equation, it's going to come out in newtons if I have MPa and millimeters squared. So therefore, I will need to put in my PRRI in newtons as well. So I'm going to do PRRI, PRINR, both in newtons, divided by 2. My FT was 5.5, KD, KST, which is my service condition factor for tension, which we determined was 0.84, KT is 1.0, and A is 1375. Okay, so that means that this side's going to come out in newtons and this side's going to come out in newtons, which means that I can add them together actually, and then I get in the end 7,200 newtons, 7.2 kilonewtons. So that is my group tear-out failure. Then for the other member on this side, so since the other side is identical, then PGR2 is the same as PGR1. So then I can calculate the total. For the brace side of the equation, PGRT for the brace is just the sum of these two for the two different braces, and I get 14.4 kilonewtons. Okay, so that's the second parallel to grain resistance check that we need to do for the brace side of the connection. The last one that we have to do now is the net tension resistance. We are getting there. We don't have splitting in the brace because all of our load is parallel to the grain. Okay, FT we already had. So this is also compared to the parallel to grain component of the force. Okay, so now we're going to calculate basically our net section. And we're going to take into account the countersink of the bolt hole. Now, we do not have to reduce the thickness for the net section to account for the countersink, but we do have to take out the piece of wood that's there. Okay, I'm going to show how that looks in a second. So the AG for these is 38 by 140. So that's the size of the piece of wood, and we get 5320 millimeters squared. Okay, so let's calculate now what the cross section looks like. And first thing we need to determine is when I'm doing net area across this section, okay, do I consider this to be one section for the purposes of net area, or do I calculate it as two different sections for net area? And of course, that's going to make a big difference because if I do it like this, two separate sections, then I have only one bolt hole per section, which is going to increase my net area greatly. Or if I have to check it like this, like if I am required to use both bolt holes, then I have obviously a much larger reduction in net area. Okay, so what is the requirement? So there is a requirement given in 12.4, and for you find it right in the parallel to grain group tear out resistance in it's 12.4.4.5. No, sorry, not there. It's found in 12.2. Okay, so where we talk about net section, 12.2.2, so 12.2.2.5.2, okay? For a bolted or lag screw connection under parallel to grain loading, staggered adjacent bolts or lag bolts shall be considered to be placed at the critical section, so they'll be at the same section, unless their spacing center to center parallel to grain is more than 8 bolt screw or lag screw shank diameters. So if this has to be greater than 8 df, actually I should say that if it's less than, well, wait a minute, if I have two separate sections, okay, so if that spacing is greater than 8 df, then we can consider those bolts as being in separate net sections. What is the separation here? It is, I believe, 70 millimeters, right? And 8 df equals 8 times half an inch, right? So that's 4 inches equals 101 millimeters. Okay, so that's no good. So these are too close together for me to be able to separate those bolt holes into two net sections, which means I have to assume basically they're on the same net section. So if I'm going to calculate my net area, I am going to look at if this is the cross section of my piece of wood. Okay, so there's cross section. Okay, I am going to cut out two bolt holes basically. One like this, and one like this. And these T's are the countersink part. Okay, so I'm going to make some assumptions for this. I mean, I've already said that the countersink bit is 13 millimeters. So this is 13 millimeters, and this is 25 millimeters. And we know that the bolt hole is 15 millimeters. And I'm going to assume that this is 19 millimeters. That it has to be 19 millimeters. Okay, so if I do that, I'm going to find my net area, which is going to be 38 by 140 minus 2 times 15 times 25 minus 2 times 13 times 19. And if I do that, I get that my AN equals 4076. And then if I find then I need to do my check for my net area. 1 minus AN over AG equals 1 minus 4076 divided by 5320. And I get 0.233, which is less than 0.25. So I satisfy my requirement. Okay, good. So I'm okay, but I'm kind of just barely satisfying it, so I'm not going to do a more conservative calculation than that. Okay, I've removed like the proper amount of net area from that section. And again, the reason I had to include, like, those bolts are not exactly on the same section, but the reason that I had to include them both in this section was because they are too close together up here. Like the bolts in adjacent rows are not far enough apart from each other in order to be able to consider them as separate sections. Okay, so now let's calculate our net tension. So our phi is 0.9. Get our modified tension strength, our size effect factor from the table of size effect factors for lumber. We get 1.3. And now I can calculate my TNR1. So I get 22.0 kilonewtons. So to find my total, I'm going to add two of them together because there are two members with the same net tension. Right, so TNR1 equals TNR2. Okay, so I'm going to put one final cut here, and the last video will be a short one where we sum up and check all of the resistances against all of the individual requirements. So in this video, we looked at all of the parallel to grain and perpendicular to grain resistances for both the beam side of the member and the beam side of the connection and the brace side of the connection.